So thank you for inviting me. So before we forget this in the rush of the contributed talks later, I would like to thank you to use the opportunity. Yes? I would like to use the opportunity to thank the 5 organizers for the work they put in and for bringing us together here in this wonderful place. So thank you. Good. So what I want to talk about is, like, in the first half of the talk is based on joint work with Get, Korob, Cook, and Matteo Vanacci, and it's about profinite groups. So, okay, we take a profinite group, G, and okay, you can think of the additive group of the ring of p-adic integers, if you like, or you can think of matrix groups over these p-adic integers, or you can think of these strange infinite products of finite simple groups Margarita talked about. So there are a lot of examples. So it's a compact, totally disconnected topological group. And we can associate a ring to it. It's called the completed group algebra. So we can take its Z hat double bracket G. So what is it? So we take G and we take an open normal subgroup, and then we get a finite group. And we take the ring Z and we divide out a non-zero ideal, and then we get a finite ring. Right? So we have a whole bunch of finite rings, and we take the inverse limit of this whole thing, where U is an open normal subgroup in G, and N is a natural number. So this will be a profinite ring. Okay, so in particular, it is again, the additive group is a compact topological abelian group, and we have a Haar measure on this. So we have a Haar probability measure. Mu is a Haar probability measure on this ring. And then you can ask a question. You can say, okay, let's pick elements at random in this ring and ask, when do they generate the whole ring as an ideal, say as a left ideal? So question, what is the probability that, let's give a name to the probability, I will write PGK, that k random elements generate this thing as a left ideal. Okay, so here's an example, my favorite example. So what is the probability that 2 random elements generate the group, the completed group algebra of the group S3? Any guesses? Okay, no idea. So it's 3 to the power 10 pi to the 8 times 13 and theta of 3. And in case you can't do it in your head, it's something like 0.398. Okay, so the talk is about where this comes from and a little bit of the story that evolved around this. Okay, so of course, this question is not well defined for every profinite group. So the important definition for us is, we will say that a group G has Uberg if PGK is positive for some K. And so now you wonder, what is this Uberg thing? What is this supposed to mean? So in order to understand, this is an abbreviation, and in order to understand, you need to know the following theorem. I proved this with Matteo already was published in 2016, but when we wrote it, we were two young postdocs in Düsseldorf. And so we found out that, okay, we define a number, Rn star Gf Q, where Fq is a finite field, to be the number of absolutely irreducible representations of G over Fq of degree n. So it's rho from G to Gn Fq, absolutely irreducible, of course, up to isomorphism. And then the statement is G has Uberg if and only if there is some constant such that for all n and q, this number of absolutely irreducible representations of G over Fq is bounded by Q to the nc. So it's exponential representation growth, but it's uniform somehow in this prime power. So that's why this is uniformly bounded exponential representation growth. Okay. Good. Okay, so examples. So are there groups that have this property? Yes, there are many of them. Okay, like finite groups, this is easy, right? So finite groups, they have representations only in a bounded set of degrees and only at most as many as the order of the group, so they have this property. But you can do a lot more. So every profinite group that is virtually, say, every finitely generated G, which is virtually pro-soluble. Yeah, so it has an open normal subgroup that is an inverse limit of finite soluble groups. And even more, you can say there's a convenient criterion. So if you have a group G and you find some finite group that is not involved in this group as an upper section. You find some finite group that you cannot write as a quotient of some open subgroup. As soon as you have this, it has Uberg. Finitely generated if G does not involve some finite group. Yeah, so in particular, this opens a lot of examples. So you take an arithmetic group with the congruent subgroup property, you take the profinite completion, it has Uberg. You take a branch group on a regular rooted tree of bounded degree, you take the profinite completion, it has Uberg. Okay, so there are a lot of these groups, but of course there are also some groups that do not have Uberg. So here's a non-example. So you take a free group on D, a free profinite group on D generators, where D is at least 2. Then, okay, what is the reason? The reason is that if you count the absolutely irreducible representations of the free group over FQ, so what you can do is, like, for every generator, you can pick a matrix, so you get roughly Q to the n squared times D, but then you have to, conjugation will give you a D minus 1 here, and then, okay, then not all of these representations are absolutely irreducible, but most of them are, so it's roughly something like this. So you see an n squared up here. Okay. So, but apart from this, and groups that project onto this or virtually project onto this, it's hard to write down groups that do not have Uberg. Okay, so, okay, now we have this class of groups, and we have this question, so we want to compute this number. What is this probability? And this is something Gerd, Matteo, and I did, and we found the following funny formula. So here's a theorem. Published in 24. And so the theorem is, so we take a group G with Uberg, then the probability that k random elements generate the completed group algebra is zeta wg of k inverse. So there's some zeta function involved, and now I want to give you the formula for this zeta function. Zeta wg of a complex parameter s is, you take the exponential, and you sum over all primes p, you sum over all possible degrees n, you sum over all powers of this prime, so j running from 1 to infinity, then you take the number of absolutely irreducible representations of G over the field f pj, you divide by j, you take p to the minus sjn, and then comes the strange thing, you multiply with the number of elements in the projective n-1 space over the field f pj. Okay, so this is surprising when we first saw this, but it's not too bad. So what is this? You somehow count absolutely irreducible representations over all finite fields, and you have to put this weight in. So this inner part here is this logarithmic series. So it's something that is reminiscent of this Weil zeta function or Hasse Weil zeta function of an arithmetic scheme. So, and the point is, of course, this converges or in some right half plane and for real part of S large if G has Uberg, and whenever it converges, this formula holds. So in when convergent. Okay, good. So I don't want to give you the proof, but somehow what the point is that all of this doesn't entirely depend on this completed group algebra. You essentially, you can project onto the semisimple, largest semisimple quotient, say over Fp, and you get a Wedderburn decomposition. And essentially, you only have to make sure that this formula holds if you look at one component of the Wedderburn decomposition, and then by some continuity argument, you can extend it to this whole profinite ring. I come to that. Exactly. So, okay, let me give you examples. Example A. Let's take the trivial group. And of course, the trivial group only has one-dimensional representations, and only one of them. And so if you plug this in, this n disappears, and you get this zeta w of the trivial group is just the product over all primes. Pull the sum out. The n has gone, and you have like x of a sum j running from 1 to infinity, 1 over j p to the minus sj. And that's the logarithmic series. So you get here the product of all primes, 1 minus p to the minus s inverse. So this is just the Riemann zeta function. Okay, so good. Let's check in another example. B. Let's take z hat, right? So the procyclic group, the free procyclic group. It's G. Then again, we only have one-dimensional, absolutely irreducible representations. So how many homomorphisms do we have into the multiplicative group of a finite field? We can take the generator to every non-zero element of the field. So we get a q minus 1 here. And if you plug this into this formula, you get this Weil representation zeta function of G is zeta of the s minus 1 divided by zeta of the S, where zeta is again the Riemann-Zeta function. Okay, and then if you can do this for finite groups. If you have a finite group where the representation theory over all finite fields is sufficiently well understood. So as an example here, if you take S3, you can write down the representations. It's very uniform for all primes different from 2 and 3. And for 2 and 3, you have to look a bit about what's happening there. But what you get is the zeta function, Riemann zeta function squared. Riemann zeta function is 2s. Riemann zeta function at 2s minus 1. And then you get some correction terms for the primes 2 and 3. 1 minus 3 to the 1 minus 2s and 1 minus 3 to the minus s. Okay, and if you use this formula and plug in 2, you get the value up there. Okay, so I want to make some remarks here. Okay, the first thing I just said, so I think of this as a non-commutative analog of the Hasse zeta function, right? Instead of counting rational points on a scheme, you count absolutely irreducible representation with some correction factor. And this correction factor is the number of maximal ideals in a matrix algebra. So I think that, strictly speaking, we're not counting absolutely irreducible representations, but somehow something related to the maximal ideals in here, because there are so many. Okay, but you asked about rationality, so what can we say about rationality? So we have an Euler product decomposition by just pulling out the P here. So zeta WGS is a product over all primes, zeta GWPS. And okay, these in general don't have to be rational, but it's hard. I mean, they are in certain cases. I will come to this. But you can do the following. You can pull out the n, and you get a factor that depends on P and n. And then something nice happens. So if suppose that your profinite group is the profinite completion of a finitely generated group gamma. What does this help us? Then this is the local Weil zeta function of an algebraic variety, namely you take the moduli space of n-dimensional absolutely irreducible representations, and you take the direct product with projective n-1 space. And so this means that these are rational. And so if you take the profinite completion of a discrete group, this will always be quite nice. For profinite groups in general, this can of course be weird. But okay, maybe the more interesting question is, when are these rational? Okay, if you have a if the degree is bounded overall for virtually abelian groups, then these will be rational. But we also found cases where this is not the case, like the Lamplighter group, and still these factors are rational. So this is something I don't understand when these parts of the Euler product are rational. But it's more than like the obvious ones. Okay, so good. So now I want to speak about the abscissa of convergence. So what is the abscissa of convergence? I said, okay, somehow it's measuring how difficult it is to generate this ring by randomly chosen elements. So the abscissa of convergence is the minimal number of probabilistic generators. So it's somehow measuring the complexity of this group. Okay, so we computed the abscissa for some examples. And after a while, we realized that something strange happening, because we could very well compute it for some groups, and we could hardly say anything for other groups. And this somehow the class of Uber groups falls into two pieces. Like there are groups where the abscissa of convergence is dominated by representations in a small set of primes, say one characteristic, and you have a huge family of absolutely irreducible representations for n growing. This is what would get called space-like. And then there's the other phenomenon where you have representations of somehow bounded degrees, but for all primes that drive the abscissa, and these groups we now call time-like. And then there's something here. I mean, there could be groups where both count, but I don't know a good example of this except for manufacturing weird infinite products of finite simple groups. And okay, so for these, it's typically easier to compute the abscissa, whereas here you run into number theory. Okay, let me give you an example. This is like the weirdest theorem I've ever proved. So if you take P to be a Mersenne prime, and you take the free pro-P group on R generators, free pro-P group, free pro-P, then the abscissa, like I will denote it by alpha W, the abscissa of this group is P log P divided by P minus 1 log P plus 1, and then you have this R minus 1, and you have a plus 1 there. And the reason is that if P is a Mersenne prime, the free pro-P group is space-like, and for P equals 2, they're also space-like. But for other primes, the free pro-P group is time-like. This is kind of surprising. I didn't expect this. And the reason is that if you have a Mersenne prime, the representation theory at characteristic 2 of these groups is somehow, there are a lot more representations in characteristic 2 than for the other cases. Okay, and so for other free pro-P groups, we have a result that depends on conjectures in number theory. So, and I want to use the opportunity to somehow explain to you a bit more about these time-like groups, because it feels like there were some number theoretic problems that already occurred for rather innocent groups, like pro-cyclic groups. And so I sat down and tried to somehow get over this problem for pro-cyclic groups, and I want to tell you what about the results. So let me. This is like the second part of my talk. It's about pro-cyclic groups. And these are the easiest time-like groups you can imagine. So what is a pro-cyclic group? A pro-finite group is pro-cyclic if it has a dense cyclic subgroup. So for instance, G is dense cyclic subgroup. And the main example you have, of course, is Z hat, and every other pro-cyclic group is a factor of this group. But you can, of course, take whatever the additive group of the ring of p-adic integers, or you can take finite cyclic groups and so on. And I want to focus on the following groups. So we take a set S, a non-empty set S of primes. And I want to look at the group HS, which is the product of all primes in S, ZP. And I want to look at GS, which is the product of all primes in S, where we take the cyclic groups of order P here. So this is the largest procyclic group, with S being the set of prime divisors, and this is the smallest procyclic group, with S being the set of prime divisors. And it's not difficult to determine the absolutely irreducible representations of these groups. Yeah, so if you want to have a representation of HS over the field with Q elements, so you have Q minus 1 elements in your field, but this generator here can only be mapped to elements whose order has a prime decomposition where only primes in S occur. So what this is like the S part of this number. So this is the largest S number dividing Q minus 1. And also for this other group here, a similar argument, how many homomorphisms do you have into this multiplicative group? So now you can only have orders that are square-free S numbers. So it's something that I call the S radical of this number. Yeah? It's the largest square-free divisor of Q minus 1, which is made out of primes in S. Okay. So now you think, okay, like for higher n at least 2, you get no absolutely irreducible representation, so it should be easy to determine the abscissa of convergence, but it isn't. Where do I write this? I want to write something here. So I have a concise conjecture. I can tell you what I guess will happen, and then I can explain to you why I believe this is true. So the conjecture is that the abscissa of GS is the abscissa of HS, and it is the same as the abscissa, let me write, of something plus 1. And what is this something? So ADS is the abscissa of the partial Riemann Zeta function. So you take the Riemann Zeta function restricted to S, and this is the product of all primes in S, 1 minus e to the minus S. So in a sense, we should be able to tell from the set exactly what the abscissa is. Okay, so why do I believe this conjecture is true? So here's a lemma one can prove. So, okay, it's easy to see that the abscissa of GS is at most the abscissa of HS because it's a factor group. And it's also not difficult to show that this is less than this abscissa of the Riemann Zeta function, the partial Riemann Zeta function plus 1. And then one can show that there's a lower bound of the following form, 1 over L ADS plus 1. Okay, and what is L? Where L is a Linux constant. What is a Linux constant? L is a Linux constant. This means there exists some constant, some positive constant, such that for all arithmetic progressions, so an arithmetic progression P, A, B, so all numbers of the form A, N plus B, say with N running from 1 and And we always want A and B to be co-prime. So for all arithmetic progressions, the least prime PAB in PAB satisfies PAB is at most A to the L times this constant. So approximately, so it's a statement about there should be small primes in arithmetic progressions, and Linnik proved that there is such a number. So this is already from 1944. Linnik showed that L exists. And of course, the number theorists started to improve the constant. And today, I think the best thing was proved in 2011 by Luris, and it's L equals 5 is possible. But there could be smaller L. Okay, so this doesn't help us at all if we put a 5 here. So, but there's a famous conjecture of a famous Indian mathematician, the conjecture of Chawla from 1934. So he knew that before Linnik proved that something like this can be true. So he claimed that, like today I would say L1 plus epsilon is a Linnik constant for all epsilon greater than 0. And if this is true, then we could approximate here 1, and all of these inequalities are equality. So if we believe the number theorists, this should be true. The problem with this conjecture is very hard. Chawla noticed that even if you extend the Riemann hypothesis, you would get L is 2 plus epsilon and not L is 1 plus epsilon. So we currently don't know how to prove this conjecture. Okay, so this was the starting point of the things I did recently, because I somehow, okay, I mean, there are a lot of questions. So first of all, if this conjecture is true, then this would mean that every real number in the interval 1, 2 is an abscissa of convergence of some pro-cyclic group. And in particular, there should be pro-cyclic groups where the abscissa is different from 1 and 2, because all the examples I have, they have either abscissa 1 or abscissa 2. So, okay, the question is, how can we overcome this problem without solving this famous number theoretic conjecture? Okay, so before I tell you how to do something in this direction, I want to, because I think it's instructive, give you a proof of this inequality, but let's say, because it's a bit easier, let's prove this inequality. So proof of 1 over L A D S is 1. So that you see where the arithmetic progressions appear in this proof. Okay, so recall that the number of absolutely irreducible representations of HS over FQ is just the S part of Q minus 1. Okay, so we can write down the log of the Weil representation Zeta function as a sum over all primes Then we have in all powers, j from 1 to infinity, we have pj minus 1 s part divided by j, and then we have a p to the minus sj. Okay, now I do some rough estimates. I say, okay, ignore the prime powers. So we have just the sum of all primes. P minus 1 s part p to the minus s. Okay, and then let's see what we can do. So it's hard to say directly, I mean, for which primes, if you have a given set S, for which primes will there be a lot of prime divisors in S in P minus 1? This is, of course, it's a question about the distribution of primes. But what we can do is we can say, okay, we care about S numbers. So let's reformulate this. We sum over all S numbers. Let's call it M in S. So it's a number, all numbers where all prime divisors are in S. Then you say, okay, we just take the least prime we can find that is congruent 1 modulo M. If we have a prime that's congruent 1 modulo M, we know at least this part will be divisible by M. So we take the least, so we take the least prime congruent 1 modulo M minus 1 S part, and we have the least prime congruent 1 modulo S to the minus S, and then of course one of these primes could be the least prime for multiple M's, so you have to divide by the number of divisors of Pm1 minus 1, but that's not too bad. The number of divisors is small compared to the number, so asymptotically, I want to go in the other direction. We get a sum here over all M and S. Then we just make this smaller by writing an M here. And here this is of order, so D of a number is always bounded by K to the epsilon for every epsilon, so we can just write P to the M1 minus S minus epsilon. And now we of course use the Linux constants. We want to somehow have a relation between this and M, and so we get that this will be sum over all M and S, and you have the M to the 1 plus 1 minus L S plus epsilon, and this is exactly the partial Riemann Zeta function at this value. Okay, and so we know that if S, so divergent for S, or real part of S, smaller than A, C, S plus 1 over L minus epsilon, but as epsilon was arbitrary, we're fine. Okay, so you see where the primes and arithmetic progressions somehow come from. Okay, so let me give you, yeah, sure. Yeah, okay, you're right. Yeah, yes, yeah. Because you can, all the terms here are positive, and so if you take it. Mm-hmm. Okay, so, okay, how can we overcome this problem that we don't know this conjecture? The point is that you have very good results in number theory if you ask about what's happening on average. Right? We cannot say for a specific thing, but on average, things are good. And so I wanted to use this. And what you can do is you can say, okay, if S is picked at random, so you choose your primes at random, how do you do that? You choose them independently, and you say the probability that a prime P lies in S should be P to the 1 minus delta minus 1 divided by P minus 1, where delta is some number you pick in the interval, the open interval 1, 2. Then the conjecture holds. So then alpha W of GS is alpha W of HS is ADS plus 1, and I can even tell you what it is. In this case, it's 2 minus delta, almost surely, so with probability 1. Right, so in particular, this allows us to answer at least one of these questions. So the corollary, every real number, every beta in the interval 1, 2 is alpha W G for some procyclic group. And in fact, by this argument, there are uncountably many such procyclic groups with this given abscissa. Okay, so but let me give you an open problem. I still fail. I mean, it's an existence result, but I still can't write down a single procyclic group where the abscissa is between 1 and 2. So give an explicit, in the sense that there's some description of the primes you put in this group, description of procyclic G with alpha WG being strictly between 1 and 2. Right, so the example for 2 is Z hat, and the example for 1 would be ZP or any finite group, but I wasn't able to write down something where I can prove that this abscissa is really strictly between 1 and 2. Okay, so let me, how many times? Yeah, perfect. So I can tell you in 7 minutes how to prove this theorem. This. What's the proof of theorem 4? Okay, let's start with the upper bound for the abscissa, because this is easy, upper bound. Okay, we take Z to be a real number. It should be larger than 2 minus delta, so it's, I look at a parameter where it should converge, and I want to prove that almost surely it does converge. So I define a random variable, yz. This is the sum over all primes, over all integers, m. And I take im m to the minus s, and im is a random variable that is supposed to be 0 if m is not an s number, and 1 if m is an s number. So what do you do with a random variable? You compute the expectation, right? So the expectation is an integral over the space where all these sets of primes live. And of course, an integral with, like, you have this positive, I want to write a z here. And you have this positive random variables, you can exchange sum and integral. So this is like m in n, and you have to compute the expectation of this IM, m to the minus z, and okay, let's see, so you get, so when is m an S number? It's exactly the case if all the primes dividing m lie in our set, so the probability is p to the 1 minus delta minus 1 p minus 1, where sum over all primes dividing m. Okay, and then you estimate this. You say, okay, like take this p to the minus delta out, and then the rest is doesn't really matter. So this, I want to say this is at most. I'm not sure if there might be a constant, so it doesn't matter. So the point is that here's the radical of m to the minus delta m to the minus z, and okay, you can show like the radical is typically, for most of the numbers, the radical will not be much larger than m, so this will converge for m, for z greater than 2 minus delta. The radical is the largest square free divisor of m. Exactly. So what I want to say is if you have a random variable with finite expectation, then almost surely the random variable is finite, right? There would be a set of positive measure where it is infinite. Their expectation wouldn't be finite. So this directly means almost surely ys is finite, and this gives us an upper bound for the abscissa. Okay, the lower bound is more difficult. So here's to lower bound. So what you do is, okay, you take a real number t, and I somehow want to do this. I want to sum over all primes at most t, and I want to take the s radical of p minus 1, and then I take p to the delta minus 1. So I go quite a bit into the direction where it doesn't converge anymore. And let's call this xt, and you calculate, similar argument as before, you calculate the expectation, and you can show that it's not difficult. Like asymptotically, there's an upper and lower bound that is the number of primes below t, so the logarithmic integral lit. Okay, so that's good, but this doesn't help us. So if you want to say something about the random variable, we have to show, or we have to understand how far it deviates from the expectation, and so you have to compute the variance, and this is the problem. So the main step, the key step, is to prove that the variance of this random variable is of order, like, let me write it like this, expectation xt squared as t tends to infinity. And so why is this the key step? Because it means that you can use classical inequalities of Cantelli-Chebyshev to say, okay, then this random variable does not deviate too strongly from expectation, but the expectation is in such a way that if you add here something less than 1, it will still, or you subtract something less than 1, it will still not converge, and you can prove that almost surely this wave representation zeta function diverges as soon as you are below 2 minus delta. And the way to do is you need a famous theorem of number theory. It's the theorem of Bombieri-Vinogradov. Which says that the number, so in a sense it says the number of primes in an arithmetic progression does not deviate too far from what you expect. So in average, the error term is somehow as good as the Riemann hypothesis would predict. And with this, you can do this. Okay, I stop here. Thanks. You mean if you have abelian groups that are not polycyclic? Yes, then I think you can. So the difficult part will be this, and if you take like this to the power r, you get an r here, but then you can use similar methods. So the difficult part, I think, is to treat the polycyclic groups and the procyclic groups. Yeah. Mm. Yeah, it might be. So I thought a bit about it, but I don't see a direct way to go back. But yeah. Yes. Yeah, you're right. So yeah, I should. I mean, we have pro-finite groups with arbitrary abscissa, and you can build them with using infinite products of finite simple groups of Lie type, because if you have a finite group of Lie type or a field with Fp, then you know the small representations live in characteristic P, and the others don't count, and you can manufacture groups with arbitrary abscissa. I mean, yeah, I think that you can extend this then to abelian, right? So taking the half power of such a group doesn't change the argument a lot, I would say. The abscissa typically goes like, the abscissa is something like r minus 1 times a constant plus 1. So it's, if this behaves well, this should just show that every real number is an abscissa of some abelian. Yeah.
Can you give the heuristic behind the connection between the probability to generate and the function?
Oh yes. Okay, so you take k random elements in this completed group algebra. When do they generate? They generate if and only if they do not lie in a maximal ideal. So how do you calculate? You have to find all maximal ideals. Okay, then you're directly at irreducible representations, and then yeah. Okay, so I can't say anything more convincing than this. So you look at this matrix algebra, one thing in your Wedderburn component. This corresponds to J absolutely irreducible representations over FQ if FQ contains FPJ, and otherwise there are none. And then you can do it by hand and then put it together. So, but it's about the maximal ideals in this matrix algebra, which you can count.
So you count the maximals of the finite index.
Yeah, I mean, there's something like this notion of like when do random elements generate is related to positively finitely generated groups that were studied by Avignon-Mann, and it was like he has a similar argument to relate it to some probabilistic zeta function, but in the group case, these zeta functions are not so nice, but here they are.
Final question for me. It's procyclic, you don't have an explicit description, but yeah, I guess you have some other groups for which in between 1 and 2 values taken.
Mm-hmm. Yeah, like if you take products of finite simple groups, then it's easier to control.
Any more questions? Let's first thank the speaker.